Hi there. We looked today in class at the mean value theorem. The mean value theorem is a way of guaranteeing a particular slope. It says that if f is continuous and differentiable on a closed interval, then we are guaranteed a point C in that interval, not including the endpoints, so inside that interval, such that f prime of C is equal to f of B minus f of A all over B minus A. So that's my mean value theorem. And like I said, it's a way of guaranteeing a particular slope. To kind of dissect this a little bit, I've gone ahead and picked number 27 from the book. And number 27 is a picture of a graph, and it asks us to locate those C's, those possible points where the mean value theorem is satisfied. And this is going to allow me to demonstrate what this is talking about. So f prime is C. Okay, quick refresher here. Derivative is the slope of our tangent line. Right, so the mean value theorem says there's a tangent line whose slope is equal to, and then f of b minus f of a over b minus a, this is the slope formula, right? Change in y over change in x, y2 minus y1 over x2 minus x1. Okay, and so this is the slope of a line connecting B and A. And so in my picture here, I have A and I have B, and if I go ahead and, sorry about that, if I go ahead and draw in the line, okay, connecting those 2 points, okay, that line right there, its slope is this second half of the mean value theorem. And so what are we going to do with that first half? Well, we're going to find where can I draw in a tangent line, where can I find a spot on the graph with a tangent line of a slope equal to the line I've drawn in here. Well, if their slopes are equal, that means they're parallel. And so I'm going to be starting here, and as I kind of walk my way around the graph, I'm going to go ahead and use my ruler to kind of demonstrate where the tangent line is going to be. As I walk my way around the graph, kind of pretend drawing in my tangent lines, I find right here at the, again, sorry about that, at the base, or almost the base of this relative minimum here, that I do have a tangent line that's parallel to my AB. Okay, and so I can go ahead and draw in, I'm going to draw it dotted so we can see the difference here. I can draw in a tangent line, okay, at that point. And because that tangent line is parallel to my AB line, this point where that tangent line touches the graph, that's my C. And I'm going to go ahead and call it C1 because in this particular graph there's actually another place as well. Right? Mean value theorem guarantees us at least one spot, but it is possible that there might be more than one C between A and B. And so I'm going to go ahead and continue from there. Right? I'm going to look at my tangent lines on this other side of the graph, and as I kind of trace my ruler, again sort of mimicking the tangent line here around the graph, I notice that right here, again right around the peak of that of that relative maximum, I have another tangent line that's parallel to my original AB. So again, I'm going to go ahead and draw this in dotted so we can see the difference of our lines. Right there, that dotted line is parallel to the original line. And so where does it touch the graph? Where is it tangent? That would be my other C. Again, there doesn't have to be more than one, but there might be. Okay, and so that's what the mean value theorem is dealing with. It's finding those two numbers, finding those two C's. Okay. So I've picked two problems to demonstrate that. The first one is number 32 in your book, which says f of x equals x times the quantity of x squared minus x minus 2, and we're given an interval from -1 to 1. This is my A and my B. And we're asked to find the values of C guaranteed by the mean value theorem. Okay. Again, the mean value theorem is this f prime of C equals f of B minus f of A over B minus A. We can only use it, though, if our graph is continuous and differentiable. And so I'm going to look at this function first and make sure that there's no discontinuity and no location of non-differentiability. Okay, and so when I'm looking at this, there's no denominator to set equal to 0. It's not a piecewise where your limit might not exist, right? So there's no discontinuity, so I'm good to go with that criteria. And when I take the derivative, and I'm going to go ahead and do product rule here, although you could distribute in. We've got 1 d2, which is 2x minus 1, plus 2 d1, which will just be 1. And so distributing that x in, we get 2x squared minus x. The 1 has no impact on that function. And so we get 3x squared minus x is negative 2x minus 2. So that's my derivative, and with my derivative there's no denominator to set equal to 0, and there is not an absolute value, so there's no cusp of either my function or my derivative, and so I'm good to go as far as the differentiable criteria of mean value theorem. Okay, so once I've checked those, I can go ahead and start using my mean value theorem, which starts off f prime of c. Well, this is f prime of x, so f prime of c is 3c squared minus 2c minus 2. Excuse me, sorry. Okay, 3c squared minus 2c minus 2. Okay, and so then once we have our f prime of c, we're then going to set it equal to, and we've got our f of b minus f of a over b minus a. F of b, my b in this case, is 1. And so I'm going to go ahead and plug that in to get my f of b, and I get 1 times the quantity of 1 minus 2, which is negative 2. So that's my f of b, minus my f of a. So I'm going to go ahead and plug in negative 1 into my f. I get negative 1 times negative 1 squared minus negative 1. So this is 1 plus 1 minus 2, which is 0, all over my b minus my a. Okay. And then at this point we're going to solve for c. Okay. So I've got 3c squared minus 2c minus 2 equals negative 2 minus 0 is negative 2. 1 minus negative 1 is 1 plus 1, or 2. And so then we've got 3c squared minus 2c minus 2, which equals negative 1. And then I'm noticing over here I've got a quadratic, I've got 2 c's, and so I'm going to want to make sure that I've set this equation equal to 0, because then I can either use quadratic formula or factor. And so I'm going to go ahead and add 1 over to this side, and I get 3c squared minus 2c minus 1 equals 0. And like I said, at that point, factor or quadratic formula, or you could use your calculator to calculate your zeros. In this particular case, if I'm thinking about, okay, what multiplies to negative 3 and adds to negative 2, I've got negative 3 and positive 1. So I'm going to go ahead and choose to factor. 3c plus 1, c minus 1 equals 0. At which point, this is kind of like critical numbers, right? We have two quantities being multiplied to equal 0. So either one is a possible c, either one is a possible 0, and so I'm going to go ahead and evaluate them separately. Add or subtract 1 over, we get 3c equals negative 1. Divide that 3, we get negative 1/3. And if the c minus 1 equals 0, add that 1 over, we get c equals 1. Okay, so those are your two possible c's, right? Think about that graph from before. Those are two possible locations where my tangent line would have the same slope. Okay. The final thing we have to check, though, is we are only guaranteed a c inside the interval. So if either of these c's falls outside the interval or happens to be the endpoint, right? Our c has to be inside the open interval. Okay, and so neither of my c's can be negative 1 nor 1 or anything outside negative 1 or 1. Well, this c equals 1 is one of my endpoints, and so I can't count it. And so the only c that I can say for sure that I'm guaranteed by the mean value theorem is c equals negative 1/3. Okay, so I've picked another one here. Demonstrate one more time. Number 35, f of x equals root 2 minus x on the closed interval -7 to 2. So again, we're going to be looking to say, okay, is there any spot where it is not continuous on that closed interval? And when I'm evaluating discontinuity, I'm looking for somewhere that would be outside the domain. There's nothing on the interval from -7 to 2 that would be outside the domain. No denominator equal to 0, that kind of thing. No place where the derivative wouldn't, or sorry, where the point wouldn't exist, like an asymptote where the limit wouldn't agree, nothing like that. So we are good on the continuity front. Then we're going to check differentiability. So let's go ahead and take this derivative. And for this derivative, this is 2 minus x to the 1/2, which is chain rule. So I'm going to bring down that 1/2, leave the guts alone, subtract 1 from the exponent times the derivative of the guts. And so I'm going to go ahead and take a moment just to rewrite this really fast. We have the -1 on top, the 2 root 2 minus x on bottom. Okay. And so for not differentiability, I mean, you might want to potentially consider that denominator, but again, I'm not worried about it in this case. There won't be anything inside the interval, and so we're good to go on the differentiability front. It's not an absolute value, so there's no cusp. And so we're going to go ahead and start plugging into our mean value theorem, which again starts with f prime of c, which is just f prime of x. F prime of c, and that equals my f of b, so I'm going to plug in my 2 here, which is my b, into my f, and I'll get 0, minus my f of a. When I plug in -7, I get 3, all over b minus my a, which is -1 over 2 root 2 minus c, which equals 2 plus 7, which is 9, and -3 over 9 is -1/3. And so there's a couple routes you can take for solving for c at this point. You could do potentially a cross product. You could multiply both sides by 3 and multiply both sides by 2 root 2 minus c in order to get those out of the denominator. But I'm going to go ahead and take a route. When I'm looking at these, if these are equal, these two fractions, well, the numerators are already equal, right? They're both -1. So I'm really only concerned about making that denominator equal, right? Because if this guy equals 3, then I'm good to go. And so I'm actually just going to pull that out. 2 root 2 minus c equals 3. Because again, the numerators are already equal, so half my fraction, if you want to think of it that way. It's not actually half, but you know what I mean, like the numerator. The numerator's already equal, we're really only concerned with the denominator. And so what would make that true? Well, let's go ahead and divide 2 from both sides. We get 3/2. The inverse of a square root is to square both sides, which will give me 9/4. If I subtract 2 over, I get 1/4. And then divide that negative, I get -1/4. And you always just want to double check, make sure, like we mentioned on the last problem, it has to be inside that interval. So if I had gotten 4, I would have been able to use it, which probably actually would have meant I had done something wrong, because you are guaranteed a C, which means somewhere in my thought process I've made a mistake at some point. But you know, if I had more than one C, -1/4 and 4, I would have crossed off the 4 because I couldn't consider it. It's outside my interval. Okay. But in this case, the -1/4 falls inside that interval, so we're good to go. That's going to go ahead and be my answer. And that's mean value theorem.